This is the final unit, simple harmonic motion. And as always, if you enjoy this content, please give us a like and subscribe. So we did this in the original video in part 2, which is the definition of periodic motion. So what is it again? It is the result of a force that acts opposite the direction of the displacement and is directly proportional to the displacement. So let's say that we have a mass on a spring on a frictionless surface. So what's going to happen is if we pull this back and we release it, it's going to go back and forth. And it's going to accelerate, and you can think about this, as it's moving out this direction, the force of the spring is going to be in this direction. So we could say that force is equal to minus kx. And because f of s, is equal to a constant times x, then we can say that f is directly proportional to the displacement x. Again, that's going to be in the opposite direction of that displacement. So it's moving in this direction, and it has what's called a restoring force, that force of the spring in the other direction. Now, when it starts to compress, now it's moving this direction, now the force has reversed and it's pushing it in this direction. So this motion of it bobbing back and forth, it slows down on the way out here, it stops, it turns around, it speeds up to its maximum at the equilibrium position, then it slows down to this other value over here. And this equilibrium, let's say this is equilibrium here, then this position would be our amplitude A, or we sometimes call that our x max. The same idea is true when we deal with pendulums. If we break up the forces of gravity on the pendulum into x and y components, then we would have the mg sine theta would be acting this way. As the pendulum swings up, the restoring force is going to slow it down in the opposite direction. Unfortunately, on a YouTube video, we can't repeat this experiment, but I do this experiment in my classes, and it's super instructive on how pendulums work. So what we do is this. We take pendulums, the mass is the same, but later you'll find out that the mass doesn't actually affect it, and we pull it back the same angle theta. And then we release it and calculate the time for it to go back and forth. Now, as you might expect, for a short length, for our L here, for a short length, it's going to go back and forth quite quickly. And when we get here, because you can think about this with moment of inertia, we have a longer length, this is acting like a point particle, it's going to take more time. The period, the time to go back and forth, is going to get longer. Now, if you collect data for a whole bunch of different lengths, what you'll find is that you get a graph that looks like this. Well, how can we analyze the slope of this line? Well, a good guess is to see if this relationship becomes linear when we square the period. And if you do that, you end up with a linear relationship. So what's that value? What's that constant? Well, that value is going to be the slope. So if you do that, you'll end up with a number, and the formula is t is equal to 2 pi radical L over g. And later, we'll do the derivation for this. But for now, we want to look at this relationship of t squared to L. So let's square both sides of the equation. And that gives us 4 pi squared L over g. So we can say that t squared is directly proportional to the length, and that the constant is 4 pi squared over g. That's going to be the slope of the line. So let's look at the acceleration of this object. So we know that the acceleration is going to be a result of the force the force of the spring, which is going to be minus kx. So if we have this object at equilibrium, that means this is the point at which the spring is at rest. So there's no force acting on it at all. So therefore, x is 0. This is our origin. So x is 0, so there's no force of the spring, so there's no acceleration. But what happens when we start to put this thing in motion and let it oscillate back and forth? This is going to be simple harmonic motion. When it gets out to its maximum position, then that force is going to be acting opposite the displacement, and therefore it's going to accelerate because we have a net force on it. Well, what's that going to be? Well, it's going to be Fs equals minus Kx, and that's our net force. So we can say F net equals Ma equals minus kx. And we can solve for the acceleration of this by saying a equals minus kx over m. We could also define that as the second derivative of position, d squared x dt squared, and that's also equal to minus kx over m. The same thing is true in the opposite direction. If we go to the side where it compresses, the force is opposite the displacement in this case. It's being displaced this way, the force is in this direction. When it reaches any position x, that acceleration is going to be minus kx over m. And we have a name for this x max. This is called the amplitude. So we can calculate where a simple harmonic oscillator is using this formula, and I would recommend memorizing this formula. It's typically not given on the equation tables, but they'll usually give you this formula in the problem. So you don't have to memorize it, but it might save you time. The formula is x at any time t. So you could actually think of this, it's not usually written this way, but x instantaneous, the x at some time t, is equal to a. Now a is the amplitude. So what is the amplitude? That is the max position from equilibrium. Now, often this is written as, in the x direction, this would be x max. If we wanted to do it in the y direction, that would be y max. But the main idea here is that this is the position at any time t, and this is the maximum position, x max, or a for amplitude. And we multiply that by cosine omega t. Omega is defined as the angular frequency. So that's the rate at which it's bobbing back and forth times t plus phi. Now, we're mostly going to leave this out, but this is called the phase shift. So what we can do is, if we have a cosine curve, for example, and it looks like that, we can get the same result if we want to shift it over, and typically we shift this over by pi over 2, to be able to put that in or out of phase with another position. So we could also write this. We could say that cosine omega t plus phi, if phi is 0, then that's going to be equal to the sine of omega t plus pi over 2, 90 degrees. And that would be a 90-degree phase shift. And that should make sense, because if we shift this graph by 90 degrees, we go from a cosine to a sine graph. Now, we learned before in the earlier videos that f is equal to 1 over t. That's the frequency, and that's the period, the time for it to travel one full cycle, one full oscillation. Well, if we multiply both sides by t, or by 2 pi, we get 2 pi frequency is equal to 2 pi over t. And we call this 2 pi frequency, that's the angular frequency. So that symbol is omega. And I would also highly recommend memorizing this formula. and this is in radians per second. So this comes up, we substitute this into other equations, and sometimes this is used by itself to calculate the period, or if we're given the period, to get the angular frequency. Why is the angular frequency important? Because we use it in our formula here for finding out the position, and you'll see that we also need this to find the velocity and the acceleration of the simple harmonic oscillator. As you've probably already guessed, if we want to find the velocity, then we're going to take our position function and take the first derivative. Why? Because velocity as a function is equal to the first derivative of position. So we're going to take the first derivative of the formula x max cosine omega t plus phi. And that is with respect to time. So to do this, we're going to use the chain rule. So we have Vt is equal to d, and then we have x max, which is a constant. So we can actually pull that out of the derivative. And then we have cosine, and we're going to do this for cosine of u. Why? Because we need to do a let u substitution because we have omega t. We don't have t. So that's going to be a let u is equal to omega t plus phi. The phi is going to go to 0. So that our du is going to just be equal to omega dt. So if we do that, we can sub in, and we'll end up with v of t is equal to x max, because we're pulling that outside of the derivative. And the derivative of cosine is, you should know this at this point, it's usually on the tables, is equal to negative sine of u. But that is du. And we need to sub back in, and this is all over dt. So our let u, we know, is omega t plus phi, and we know that our du is omega dt. So subbing that in, that gives us x max times negative sine of u, but now what's u? U is omega t plus phi. And what's du? Well, du is omega dt, and all of this over dt. So our dt's cancel, our omega can come out front, and that leaves us with v of t is equal to negative omega x max sine omega t plus phi. I would study this process, this chain rule, because this whole thing, starting from here and working your way through the chain rule, is going to be something that's very commonly asked in questions, and you need to be somewhat quick at it. So what are they going to do? They're usually not going to ask you to do this as a derivation by itself. They're going to ask you to put numbers in. And what numbers are they going to put in? They're going to give you the amplitude, which will be x max, and they'll give you omega, which is the angular frequency. And then you just do your chain rule to get your answer. So you probably also guessed where we're going after this. We have a formula for the position of a simple harmonic oscillator. We have a formula for the velocity of a simple harmonic oscillator. But what about a formula for the acceleration of a simple harmonic oscillator? Well, how are we going to do that? We're going to take the first derivative of velocity. And again, this is going to be the same process that we did before. We're going to take the derivative, this time of velocity, which is negative omega x max, that's our amplitude, times sine of omega t plus phi. Where did this formula come from? We just derived it. So that's going to be with respect to time, and this is a constant, so we pull this constant out in front of the derivative, and then because we don't know sine of t, we have sine of omega t, we have to do a let u substitution. So we're going to set this up as a equals negative omega x max That's our constant, and that's going to be the derivative of sine of u. And our u, we're going to say, is omega t plus phi. When we do the derivative of u, that's going to give us omega dt. So now, whoops, I left out the dt. Now we can sub in. So that acceleration is going to be equal to negative omega x max. And then what's the derivative of sine? Derivative of sine is cosine, so that's going to become cosine of u du divided by dt. So subbing in for our u, we have u equals x max cosine. Our u is equal to omega t plus phi, and that's times du, but our du is now omega dt all over dt. So our dt's will cancel. We can bring our omega over here to become omega squared, and that's our formula for acceleration. This is going to be negative omega squared x max times cosine of omega t plus phi. Once again, we have a formula, like before, to find the acceleration at any time t. They rarely write it this way, but I like to think of this as the acceleration at any moment t. Doing these derivatives is super important. So we did it as a derivation, but you need to be able to do this relatively quickly with numbers in it. So let's just make up a position formula. So we'll say that x is equal to 10 cosine 5t. So with this, we're saying that our phase shift is 0. Almost all the problems that we do, the phase shift is going to be 0. So we have 10 cosine 5t, that's our amplitude or our maximum position, and 5 is our angular frequency. So let's take the first derivative. So that's going to be dx dt is equal to, and then I can pull the 10 out front. So then that's going to become 10d of cosine u du. And that's all over dt. Well, what's our u? We're going to let u equal 5t, and we're going to take the derivative of both sides, which is going to be du is equal to 5 dt. So we can take the derivative of cosine of u, and that's going to be negative sine. So dx dt is our velocity, that's v. I'm going to bring that minus sign out front. That's going to be minus 10, and then that's going to be sine of u. Well, what's u? U is 5t. And we have to multiply that by du. Well, what's du? That's going to be 5 dt. And that's all over dt. So we can cross out the dt's, and our 5 can come out front. So our velocity formula is equal to minus 50 sine 5t. Let's do a different problem. This time we'll do velocity, and we're starting from scratch here, so this is a new formula. So we're going to say that the angular frequency is 3, and we'll say that our x max, our amplitude, is 1, and we'll do a phase shift of 0 again. So we're going to start with our velocity formula, which we know is negative omega x max sine omega t. So what can we do? We can throw our numbers in. So our negative omega, that's going to be negative 3, times our x max, which is 1. And then that's going to be the sine of omega t, which is going to just be 3t. So if we want to find the acceleration, we have to take the derivative. So that's going to be dv over dt. And that's going to be equal to our minus 3, so we can pull that out front, minus 3, and then our derivative of sine, in this case we're going to call that u again, du, all over dt. Whoops, that's not du, that's just d. The derivative of this. And what is this? Well, our u, we're going to say, is 3t. That's our let u. So our du is going to be 3 dt. And then we can do our derivative of sine u du, and that's going to be cosine of u. dv dt is our acceleration. So now we have minus 3 cosine of u. Well, what's u? U is 3t. And then multiplied by du, which is 3 dt. And that's all over dt. Our dt's cancel. We can take this 3 and bring it out front. So what's our acceleration? Our acceleration is minus 9 cosine 3t. So be sure to practice this. This is the chain rule. You should learn this in calculus, but make sure that you can do this relatively quickly, just like you're able to do derivatives when we did kinematics. So far, all of our formulas have depended on time. Well, this is a powerful derivation that we can do to get a new formula that doesn't depend on time. It depends on position. Well, we already know that the formula for acceleration is negative omega squared x max times cosine omega t plus phi. And we know that x is equal to x max cosine omega t plus phi. So the way that we're going to do this is we're going to sub in x max in here, and then our times will cancel out, and we'll be left with a formula for acceleration that is non-time dependent. So if we want to sub in for x max, the first thing that we need to do is get x max by itself. So we're just going to divide through, so that becomes x over cosine omega t plus phi. And then we're going to take this x max and plug it in here. So that's going to become a is equal to negative omega squared. And then what's that multiplied by? Well, this right here. So that's going to be x over cosine omega t plus phi, all multiplied by cosine omega t plus phi. Well, what's going to happen? These are going to cancel out, which means we get rid of time. And we're left with a is equal to negative omega squared x. Notice, this is not x max. This is any x. So as long as we know the position at any time of the oscillator that's going back and forth, and we know omega squared, or omega, then we can get the acceleration at that position. So it's position A is directly proportional to x. Actually, it's going to be negative x, right? Because it's opposite. And we can also say that A is directly proportional to the omega squared. I shouldn't have written it like equals. I should have just said proportional to. The same idea, that A is proportional to negative x and A is proportional to omega squared. This formula is typically given on the tables, but doing the derivation will help you to see the relationship that you're going to need to do on a lot of different types of problems. So let's start out by saying that the net force on a spring, and this is the same problem that we've dealt with before, which is a spring with a mass that's oscillating back and forth, that F net is equal to ma, and it's frictionless, so the only force that's acting on it is the force of the spring, Fs. So we can rewrite that as ma is equal to minus kx. But what's the position? Well, the position, we know x is equal to x max. You can see how important these formulas are, which is why I recommend memorizing them, omega t plus phi. And we know that the acceleration, we already know that, is negative omega squared x max cosine omega t plus phi. So if we sub these in, what do we get? Well, we get m times negative omega squared x max times cosine omega t plus phi is equal to minus k, and then our formula for position, which is x max cosine omega t plus phi. And a whole bunch of stuff drops out. So we get rid of the x max, and we get rid of the cosine omega t plus phi's. So what does that leave us with? Well, that leaves us with negative m omega squared minus k. And get rid of the minus signs, and we can rewrite that as omega squared is equal to k over m. This part is super important because this gives us a relationship for angular frequency, and that's related to k, the square root of k over m. But we also can remember from before that omega is 2 pi over t. So we're going to work in this t so we can figure out the period, the time it takes for this to go back and forth. So if this is true, then if we square both sides, we get 4 pi squared over t squared. And we can say that 4 pi squared over t squared must be equal to k over m. We're just substituting that in. So rearranging, we have t squared equals 4 pi squared m over k, or the formula, which is t equals 2 pi radical m over k. So what does this tell us about this mass on the spring that oscillates back and forth? Well, as it oscillates back and forth, the time it takes to go back and forth depends on the mass, and it depends on the spring constant. As the mass goes up, more mass, then it's going to take it longer to go back and forth. And that should make sense. It's harder to push on it. It's harder to accelerate it. And if the spring constant goes up, the time goes down. A stiffer spring will make this oscillate more rapidly. So here's the derivation of the period of a pendulum. Now, a pendulum technically is not a true simple harmonic oscillator. It only approaches a simple harmonic oscillator if we deal with very small angles theta. So if we were to pull this up really high, its period would not obey this formula. So for small angles, we know that the arc length that it's spinning is going to be very close to x. So we can say we know that that arc length, s is equal to r theta. Well, we know that that arc length for this little tiny angle in here is very close to x. So we can say that that's equal to x when this is small. So if we want to look at this for this small angle theta, we can say there's a relationship between x and L, and that is opposite over hypotenuse, or sine theta is equal to x over L, and we're going to need that in a minute. So let's look at the forces. We have F net equals ma. Well, what forces are accelerating this? Well, that's the force that is perpendicular to this force of tension, and that's going to be the component of the force of gravity, which is going to be mg sine theta. So we can say ma is equal to mg sine theta, and this force is opposite the displacement, so we need to put in a minus sign. So we cross out the masses on both sides, and we're left with a is equal to minus g sine theta. Now, this is where this comes into play, because we have theta in terms of the position that it's moving and the length of the pendulum, which is length L. So let's take that and sub that in to sine theta. So that gives us a is equal to minus g, and then we have our sine theta subbed in for x over L, and we know that acceleration is negative omega squared x max cosine omega t. And we also know that this x right here is equal to x max cos omega t. So if we sub those in, we end up with negative omega squared x max cosine omega t, and we're saying phi is 0, minus g over L x max cosine omega t. So we have cosine omega t's go away, our x max goes away, our minus sign goes away, and we're left with omega squared equals g over L. Now this is important because this gives us a formula for for angular frequency. Now, just like we did in the derivation for the mass on a spring, we know that omega is equal to 2 pi over t. So therefore omega squared is equal to 4 pi squared over t squared. And we can just sub this in for omega squared. So that gives us 4 pi squared over t squared is equal to g over L. And rearranging that, we end up with the formula t is equal to 2 pi radical L over g. Now, what's important about this formula? As the length of the pendulum gets longer, the time it takes to go back and forth is going to get longer. T squared is directly proportional to L. So let's make up a number. Let's say we made the length 4 times as long. That's going to make the period twice as long. And gravity on a planet, as the gravity goes up, the strength of the gravitational field, then the period is going to get less. And you can picture that this is going to swing back and forth more quickly as gravity has a greater force on it. And if we were in space where gravity was 0, the period would end up approaching infinity. It would take essentially forever before it completed one cycle because there's nothing pulling on it at all. Now, there's one last thing that I want to mention because this has come up on the AP exam. I've only seen it once, but it's a formula to figure out at any angle for this instantaneous angle, that's equal to theta max sine omega t. Now, the derivation for this involves Lagrangian mechanics. And this, I don't know why they put this on the AP exam, because this involves partial differentials. So this would be something that you would be doing probably at the end of Calc 2 or maybe in Calc 3. So I really feel that this is outside the scope of the class. However, I'm going to put a link in the description so that you can see how to do this if you're interested. Otherwise, I wouldn't worry about it. So we've done this derivation for a mass on the end of a string that goes back and forth, but that's a point particle. What if we have something that is like a meter stick that's at the end and that swings back and forth? Well, the mass isn't all concentrated at the end, so we need a different formula. And usually this formula is provided on an equation table. But the formula is 2 pi radical I, the moment of inertia, over mgl. And L is from the pivot to the center of mass. So let's go ahead and just do this really quickly for one example. It's a pretty easy formula to do this for. But let's say we have a rod of length L, and we want to figure out the formula for the period. Well, all we do is put in 2 pi, and then what's I? Well, that's the I of a rod spinning about its end, and we know that that is 1/3 ml squared. And then we put in our mg, and what's our L? Our pivot to our center of mass is L over 2. So we put in our L over 2. And what does that give us? Well, when we rearrange and do the math, that gives us 2 pi radical 2/3 L over G. So it's pretty simple. But let's do this one more time, but let's do it for a pendulum with a mass at the end of a string of length L, because you're going to see what happens, because this is acting as a point particle. So our formula is, again, T is equal to 2 pi radical I over mgl. And what is I in this case? Well, that's 2 pi radical I of a point particle is mr squared, and our radius in this case is L, so that's ml squared, divided by mgl, and where's the center of mass? It is L away, so that's just L, and one of our L's will cancel, our mass will cancel, and as we would predict, T comes back to 2 pi radical L over G, which was the formula we derived before. Okay, this is very interesting. Let's say we have a position of X as we've done before, so that we have a simple harmonic oscillator that's oscillating back and forth like this. But then we also have a Y oscillation. So we have it oscillating in this direction as well. What is that going to end up producing when we put those two together? Well, let's look at the velocity. If we take the derivative of this and the derivative of this, we know using the chain rule, I just skipped ahead because you should know how to do it at this point, we end up with this formula here. So when is the velocity at a maximum? The velocity is at a maximum when this becomes 1. That's the largest that can become. And when does that happen? When this value right here becomes pi over 2. So when we're at pi over 2, which is 90 degrees, then this velocity reaches its maximum velocity. And this value right here is V max. And the same thing is true here. When this becomes a maximum, when this becomes 0, because that becomes 1, and again, this becomes the maximum velocity here. So we can see that as this oscillates from 0 to pi over 2 to pi to 3/2 to 2 pi, as it goes through that oscillation, this value is its maximum, and this decreases while this increases. So what kind of pattern or shape do we end up getting? Well, we end up with a circle. And think about it this way. If we have an observer from the side watching this X go back and forth, because as this goes around, it looks like to this person like a mass that's going back and forth. It reaches its maximum here. And then to an observer from the side, this is reaching its maximum at this point. And if we pick any other point from here, this has both X and Y. And if you put the numbers in, you'll see that this value for velocity, our V max, at any point is the same. Well, what happens to an object if you have a fixed radius r and the velocity is the same? You get a circle with a constant acceleration and a constant velocity. And we know that that acceleration is going to be equal to minus omega squared x, where x is what? Well, x is going to be the amplitude. And what's that amplitude? That's going to be the maximum position. And the entire time, that amplitude is r, and that's constant, so the acceleration is constant. Now, a really instructive way to do this is to look at a little bit of computer programming. So we're going to look at a JavaScript code that is going to be able to be manipulated so that we can see the results of these two formulas put into practice at the same exact time. Okay, what we have here is a JavaScript file, and it's pretty cool. If you want to mess around with this, you can copy this code into Notepad++, it's a free program for PCs, or TextEdit, which is built into Macs. And you save that file as an HTML and then open it in your browser. So you don't really have to worry about any of this except for this line right here. And what this is our x position. So I called it pos x, just short for x. So in this equation, that's our x here. So what's the next value? 2 times amplitude x. So that is our x max. And then we have math.cosine. That just gives us our cosine function, which is omega t, which is our omega going to be 0.1. And then the 1.57, which is going to be pi over 2. Pi over 2 is 1.57, so that's going to start our animation in the center. So if I reload this, our animation starts right there. The 200 you don't have to worry about. That's 200 pixels, just moving it so that it doesn't oscillate off the screen. So what happens when we have this position x formula? It moves back and forth from 0 to 2 pi with an amplitude of 2 on either side from the equilibrium. But what if we want to know how fast it's going? Well, we're going to take the first derivative of this formula right here. We've done this multiple times at this point, and that gives us a velocity of x of negative 0.2 sine 0.1 t. Now, what's the significance of this 0.2? Well, that's going to be our maximum velocity, and that's going to occur when it crosses equilibrium right here. But what happens if instead of doing this in the x direction, we do this in the y direction? So I'm going to comment that out, and I'm going to save my file and refresh it. And you're going to see that now we have a simple harmonic oscillator acting in the y direction. So that's exactly the same as what we've done before. It's offset, so it's pi over 2 different than the x component, because if we let both of these happen at the same time, then you can see that when we have x oscillation this way, that's simple harmonic, and y oscillation this way, that's simple harmonic, when we put those together, we end up getting a circle. And that circle has a radius, which is 2, that's right here, and it has an angular frequency that is giving us a velocity of 0.2, and down here 0.2. So these are the maximum values when it reaches equilibrium in each position. So this is the x, this is the y. But as the x decreases, the y increases. So what's actually happening is that we have a constant speed of 0.2, whatever units that is. We could say meters per second.